Alright, so I want to do one more on op amps before we move to, some other uses of op amps. And I want to do it in a way where we sort of find the equations of motion. That way I can use this for two different classes. So you can use this for controls to find the equations of motion, and you can also use this for instrumentation to learn how to use op amps for electrical measurement signals. So I'm going to assume that you walked into this video without watching my previous video. So op amps are short for operational amplifiers, and the symbol for an op amp is this triangle. There is a negative terminal and a positive terminal. There are also two positive and negative terminals here for the power supply. It's not shown in this diagram. And basically, these positive and negative terminals act like a voltmeter, and they measure the differential between the positive voltage and the negative voltage. You assume, there are some assumptions here. The assumption is that the impedance of the op amp is infinite, and so no current runs through here. So no current runs through the op amp, or the left side, and therefore the differential across the two voltages is zero. The assumption, though, is that the gain of the op amp is infinite, and so even though the differential of the voltage is zero, the gain is infinite, and so the output is equal to this VO here. In these two op amps here, there's a feedback loop. One of these has a capacitor, has a feedback loop, and one of these has a resistor. And so the resistor and the capacitor are swapped in these two examples. And these op amps look very, very similar, but you'll see in the derivation that it actually, they come out to be two completely different things, which is actually kind of crazy if you think about it, because if you buy an integrated circuit, there will be like a couple pins on it. It looks like those little insect bugs, and if you just pull out the resistor and the capacitor and swap them just willy-nilly, like you'll completely change what the circuit does, which is kind of interesting. Anyway, the derivation for the equations of motions of these two op amps, and I didn't write down what they do until the end, and you can obviously read ahead if you want, but if you don't want to do that, don't look down. So you can see that, like I said, just swapping those two elements changes a lot. I wrote down the electrical elements here. So the voltage differential across a resistor is current times resistance. In a capacitor, it's different. You have a voltage. The derivative of the voltage is actually equal to the current, and so you can kind of look at this the other way, and if you integrate both sides, the voltage in the capacitor is equal to the integral of the current. So basically, if you supply constant current to a capacitor, it will basically fill up until it can't fill up anymore, and then it saturates, the voltage becomes constant, and the current drops to zero. And then at the same time, though, if you remove the current source from it, now you've got a way for the current to flow, and it's like opening the valve on on a bucket with the valve, right? And it just will empty the water, if you will. Alright, so let's get this started. So the positive terminal on both of these is ground. I'm just going to do one at a time because I think it's going to be confusing if I do both. So the positive terminal on this guy is grounded, so that means the voltage of the positive terminal is zero. Since the voltage differential of the two is equal to zero, it also means that the negative terminal is actually grounded as well. And since the negative terminal is connected to this point A, this junction here, we can write that the voltage at point A is zero. And that's a useful result that we'll use later on. At this point, you need to decide whether or not you want to use KVL or KCL. I like to just try both, but I like KCL first, the current law, just to make sure that I can see where the currents are going. And so I'm going to say that the current running through the resistor is IR, the current running through the capacitor is IC, and the current going into the op amp is I minus. And so IR equals I minus plus IC, but I minus is zero, right? The infinite impedance doesn't allow any current to flow into it. And so that means that the current flowing through the resistor is the same as the current flowing through the capacitor, and I'm just going to call it I. I'm going to remove the subscript since it flows through both. At this point, I can take a look and I can say, okay, since I know the current is the same running through both, I'm going to create two equations where one is the voltage differential across the resistor is equal to IR, so that's VI minus VA is equal to IR, and then the voltage differential across the capacitor, so VA minus VO, and in this case you have to use the equation dV dt CI, so you have to take the voltage differential, the derivative of that is equal to current, and basically you set these two equations equal to each other, and you know that VA is zero, And so you just get the negative pops out, and then you substitute in the current relationship here from the resistor, and you end up getting that the output is actually a differential equation where V out dot, so the dot on top is a derivative, and so V out dot is equal to negative VI over RC. And so what you can do is you can think of it just like this. You could integrate both sides, and you can basically say that V naught is equal to the integral of VI over RC. And so basically what's happening is that if VI is a constant and it's negative, the voltage in the output is going to be a line where the slope is VI over RC. So you can actually use this later on in an analog to digital converter, because what you can do is you can apply a constant voltage input, or you'd call it a reference signal. You can apply a reference signal to this op amp, and it will slowly increase the voltage. And then what you could do is you could take that increasing voltage and the voltage that you're trying to convert to a digital signal, and you can compare those two. And when the integrating circuit is above or greater than the input of the analog signal, you can stop it and then save the digital number. And I'll go into more detail on that later, but basically, this is a useful thing because you can integrate a signal and you can get the slope of that signal very easily from the equations of motion. So now let's look at what happens if you just swap those two elements. The first three equations are the same. This is grounded, which means this is grounded, which means the voltage at point A is grounded. The difference is that now the current running through the capacitor is over here, and then the current running through the resistor is over here. And so now IC equals I minus plus IR. Okay, that's actually the same. I'm sorry. The current swapped here, but you end up getting the same result. And the same result is that the current running through the capacitor is the same as the current running through the resistor. So I apologize. So the first four equations on both op amps are the same. Where things get different is where you look at the voltage drop across the capacitor. Now you've got VA minus V naught is equal to IR. And so VA is 0, and so you get the current is negative V naught over R, when in this case you have VI over R. So in this case you have the current is equal to the output voltage divided by resistance. And then if you look at the current running through the capacitor, you do the same thing. VI minus VA, take a derivative of that times C is equal to the current running through it. And then you take equation 5 and equation 6 and you put them together, and then you combine like terms. And then again, we're trying to get this into a transfer function, right, where the input is VI and the output is VO. So same thing on this side, the input is VI and the output is VO. Now when you combine equations 5 and 6 and you do sort of the algebra to get everything to work, instead of having V out not dot, you actually have the derivative of VI times negative RC. So in this case, if you put in an input signal, the output is the derivative of that input signal times RC. And so that's completely different from the other one. So in this case, you put in a signal and it's going to integrate that signal. In this case, you put in a signal and it's going to take a derivative, which is, in my opinion, really neat that you can just swap those two elements and go from there. Okay, so this is all I wanted to talk about in this video on integrating and differentiating op amps, on how to get equations of motion and how to set them up using these assumptions. These assumptions are very, very useful, so I would make sure to write these down somewhere, like on a formula sheet or something like that. Like these equations would be very useful. And honestly, if you have room on a formula sheet, I would just put these two examples on there. That would really help out. Anyway, I hope you enjoyed this lecture, and I'll see you in the next one.